So let's start.
Yes, so hello everyone, and thank you for staying with me until the last lecture. So the plan for today, so to finish what we wanted to finish for the whole week. So I will give you the new algorithm to compute representative sets, and then after that I will use this algorithm and the representative sets to obtain several polynomial kernels. So on Wednesday, I stopped after stating the following theorem. So let me just repeat this theorem once again. So the theorem is, there is an algorithm that for a given matrix M over a finite field G of S, which represents some matroid M of rank K, and then so we also have a family A of sets of size small a, which are independent sets in matroid, and we have an integer b, and then such that the sum of a and b is the rank of the matroid. Then for this input matroid, integer, and set of and family of independent sets, so we have an algorithm which computes a b representative family a prime of this set, and the size of this representative family is at most a plus b choose a, and the running time of this algorithm is this, the cardinality of the family a times a plus b times b power omega, where omega is the matrix multiplication constant, and then plus a plus b choose b power w or power omega minus 1. This is the first algorithm which I give you out of several, which really runs in polynomial time for all possible values of a and b. Okay, so let's start proving the things, right? Okay. So the main idea, well, so the proof is based on an exterior algebra, or called Grassmann algebra, but this is something which you don't see, and I definitely, so if you know what is exterior algebra, that's very good, because then you will find the things which you already know, and which you, or at least which looks familiar to you. And if you don't know, don't worry. So I will never use the word exterior algebra on any slides further on. Okay, so what is the main idea? So the main idea, so why do we care so much? Why we need the matroid to be linearly independent? Why we need the to represent sets as vectors and then speak about linear independence of sets? So why all this hassle? And this is the main reason why we have to suffer, why we have to move to algebra, because the following observation is crucial for the proof. So if I have two sets A and B, which fits, and if A fits B, you remember, right? So what does it mean now in our language that the set A fits B? So it means that the set A and B are disjoint, and also that if I take the union of A and B, then A and B, this union is an independent set in the matroid, right? And then the observation is the following. So if I take these two matrices, well, this is matrix with A columns, and let's just think that the number of rows in this matrix is A plus B. And then I take the matrix B with B columns, and with A plus B rows. Then the following statement is equivalent to the statement that A fits B. So A fits B if and only if the determinant of the matrix obtained by putting matrices MA and MB together, if this determinant is not equal to 0. Well, why, right? So in one direction, right? Suppose that A fits B, right? Then A fits B, it means that so A and B are disjoint. So in the matrix I have A plus B different columns. And also I know that the union is independent, right? So all these columns are independent. Well, if I have a matrix and with all columns are independent, so it's the full rank matrix, determinant is non-zero, right? In the opposite direction, suppose that the determinant of the matrix is non-zero. First of all, it cannot happen that this matrix has two columns which are equal, right? If it has two columns which are equal, then determinant is equal to zero. No, right? Okay, then all columns are different, but also because determinant is non-zero, all the determinants, I have A plus B rows, I have A plus B columns. It means that this is again full rank matrix, which means that all columns should be independent. Right? So this is an easy observation, but it will be very crucial for us. Okay, so the other thing, since we start speaking about determinants, right, we need to find the way how to find determinant, and the standard thing which you use in the first course on linear algebra is the Laplace expansion. And here, so Laplace expansion says that, well, if you want to compute determinant of a matrix, right, so you just take any row and do and for this row make the Laplace expansion, right? So the determinant of the matrix is equal to this sum, where this is an element with coordinates I and j, and this is the minor, right? This is the matrix which is obtained if you remove the column, the j's column and the ith row from the matrix. Yes. So and this is the standard way of computing the determinant of the matrix. Yes, there's some questions. Okay. Okay, so the question, okay, so I will stop for a question. Why can you assume the length of which vector is A plus B? For the uniform matroid, assuming A plus B makes it trivial. Yeah, yes, of course. But why I can assume that the length, look, so for my applications, that will be perfectly fine. So for the uniform matroids. So if the if I cannot construct a representation of where the vector lengths are A plus B, I have to do a little bit more things. So it's still possible to do, but no, that's the correct version. But so far, for me, it's I just want to deal with the matrices with the A plus B rows. That's and that for that. Yes, yes, definitely. So the question is again, you have rank A plus B for sure, but getting a square matrix is the issue. Exactly. So you have to truncate. So the matroid, you have to do the different things. So far, I just don't want to speak about this at all. So it's like a yes. So yeah. Okay, so we need another fact from the from linear algebra. It's called, and also I will not prove this fact here as well. So, but we will use the thing which is called generalized Laplace expansion, and this is so what is this? It's again, so how to compute the determinant. Also, if I have two matrices, one matrix with A columns and A plus B rows, and the second matrix with B columns and A plus B rows. And then, so how to compute the determinant of this matrix? Well, so this is the following formula, and in this formula, what I'm doing, I'm going from all sets of rows of size exactly A. It's here, right? And then I compute here the determinant of the matrix induced by I rows, submatrix of matrix A induced by I columns sorry, I compute the determinant of the matrix of submatrix MA, which is induced by rows with indices from I, and then also I compute the determinant of the matrix obtained from the matrix MB by the complement of the rows of I. So the I bar, so if I have a set of rows I, then I bar is the complement of the, or if I have the rows I, then the I bar is the set of the remaining rows in the matrix. So here, so again, so in this formula, what I'm doing, I go through all rows of the, or through all indices of corresponding to the indices of the rows of size exactly I. Then I take the product. This is determinant of the matrix induced by the rows from I, submatrix of A, and this is the submatrix of an B induced by the complement of the rows from of I in B. And here I take the, so -1 into the power, and here is the sum of I. This is just the sum of indices from the set I, right? And the only thing which we care, of course, is if it's even or if it's odd. Okay, and this is just the formula. So if I have these two matrices, so how what is the determinant of this of the new matrix? I can just compute it with this formula. Okay, so but look, so this is the idea. This is the technical part which I will be using. I need just one more idea, and the idea is so. First of all, I just let me just enumerate all subsets of the rows of the matrix, right? So our matrices have A plus B rows. So I just enumerate all subsets of the rows of size exactly A, right? So then I will have this L subsets, and where L is A plus B, choose A. Yes, now what I'm doing, for every set A from the family, so this is a set of size small a, I define a vector in the space RL. So once again, L is a huge number. It's A plus B, choose A, right? So for every set A, every set I identify with a tremendously large vector, right? And every coordinate in this vector, so the ith coordinate of this vector is exactly the determinant of the matrix MA induced by the set with the set I with index I. Right? So I have, again, I have A plus B, choose A different subsets, and for each of the subsets, I put here the value of the determinant in this vector. So this is a really huge vector. Okay, and I do the same thing for vector B. So the only thing that for every set B, I define the vector V bar, and this is again the vector in dimension L, and every coordinate of this vector is equal to the determinant of the matrix B induced by the complementary rows of the set for the set A for the set I. Right? And finally, I need this number sigma I, which is just -1 power the sum of the elements and the numbers in the set AI. And now, actually, so another observation is, look, so we already observed, right, that the set A fits the set B if and only if the determinant of this matrix is non-zero. Right? This is already was observed. And now the next observation is that actually, so if I use generalized Laplace expansion, then so just if I write down the sum of every determinant here, so I will obtain exactly the sum of the products of the sigma I, Vi of A, this is the vector, the coordinate here, and the Vi bar B, this vector, right? And this is again, it's there is a, it's just I'm doing manipulations with numbers, and just or that's just the way how I define these vectors, right? So every coordinate in the vector corresponds to some determinant for some subset, right? So when I just take the product of these guys, so this is exactly what's happening here. And sigma I, it's taking care of this of this number -1 power sigma I. Right? Okay. So look. So the main idea of the construction is I'm speaking about sets one set fits another, right? Okay, then actually what I realized, right, that if this one set fits another, it's sufficient just to compute the determinant of some matrix. Now I'm saying, okay, but if I'm just write down this determinant of this matrix, or if I rewrite the Laplace expansion as just sum with some of the, it's a kind of product of two vectors, right? And then, so the only thing which I care if this sum is 0 or not. Yeah. So then what we know, right? So we know the matrix M for sure, right? We know the set A, so definitely we can construct all vectors Vi. What we don't know is the set B, right? Because the set B is something which we should react for every set B of size B. So this is what we don't know, and this is the vectors VB bar. This is also something which we don't know. But what we really care, right? So what we really care if this sum is 0 or not. But if you look at the vectors VI, VA as the vector space, right? So, and then, so what you really care, right? So you have a vector VB, it comes, so the only thing you have to check if it's orthogonal to the space or not, right? Nothing else. But then the idea is why on earth and then this is the only thing which you have to check, right? So if the new set B comes, so if the vector is orthogonal to the space or not, right? But for that information, to get these answers, you don't need to keep all vectors in the subspace. So the only thing which is sufficient for you is the basis, right? So then the idea is, well, I don't want to keep all vectors VA for all sets. So the only thing which I want to keep, I just want to keep the basis, right? And because all vectors are in the space RL, and L is A plus B choose A, it means that the size of the basis will be A plus B choose A, and if this works, I will have a representative set. So this is the idea, and this is why we had to suffer so much to move sets to the matroids, to speak about linear representations of matroids, just because when we speak about vectors, we have determinant, we speak about spaces, and things become quite, and then we can select the basis. Okay, so then the algorithm is entirely simple. So the algorithm is compute the basis A prime of all vectors Vi for all i's in the family. And it's better to compute the column basis just because so I still want A prime to be the subset of A. Yeah. Okay, so this is this is the algorithm. So again, and as usual, we have to check why the algorithm is correct, why it computes the representative set, and the second thing we have to check what is the running time of this algorithm. Okay, let's start from the easiest part. So what is the running time? Okay, so what we do for the algorithm? First of all, we compute the set of all vectors VA, right? So every vector VA, what we are doing, we compute for each of the coordinate, and the number of coordinates in this vector is A plus B choose A, right? We compute a determinant of a matrix of size A times A, right? And take it for granted, right? So we can compute a determinant of a A times A matrix in time A power omega. Yeah. Now also, so when I compute, yes, so then the total running time to compute all such vectors, right, is just the size of the family A times I spent for computation of the entry A for each of the entries. So for each of the vectors. So that was one thing, right? So this is the time it takes for me to compute the set. And and then so I need in this set I need to compute the basis of this, or if you view it as a matrix, the time required to compute the column basis of this matrix. Well, I have so if I have an n times m matrix, then again take it as a fact from linear algebra that I can compute the column basis of this matrix in time m times n power omega minus 1. Now I have the matrix with a columns, and I have a plus b choose a rows. So then it means that the running time to compute the basis is the cardinality of the family a times a plus b choose a power double, so omega minus 1. Yeah. Okay, so there's a question. You don't care about sigma since this is just a fixed scalar transformation, flip signs of 1/2 of the coordination, right? I'm not sure I understand the question actually. So you don't. It's like because at the end I still need the equivalence relations, right? A fits B, then determinant is non-zero, and then this is a. Okay, maybe just we take it offline because yes, it's like a. Yeah. Okay, so then now about the correctness. First thing, so the correctness. First of all, what is the size, right, of the computed set, right? Because we claim that the size of the computed representative family A prime is A plus B choose B, right? And yes, this is so I have a matrix with A plus B choose B rows and A columns, right? So the rank, the row rank of this matrix, it doesn't exceed A plus B choose B, and then so yes, so it means that the rank is at most A plus B choose B, and that means that the size of the basis is also A plus B choose B. Okay, so then the most interesting question, right? So why A prime B represents the family, the whole family A? Well, so let's just try by definition, right? So what means that this A prime B represent A, right? It means that if there exists that for every B such which fits some set A, there should be some set A prime from the representative set which fits B, right? What does it mean that B fits some A, right? Well, it means by our arguments that this sum is non-zero. But now I'm using the fact that the set A prime is the basis of the set A, right? It means that every vector VA could be represented as a linear combination. So this is what I write here, right? And then I just move I'm just reshaping this formula. I move the coefficients lambda A here. And now what I have, look, so then I have some summons, right? And I know that these summons are non-zero, right? But then at least one from these guys should be also non-zero, right? If all of them are zeros, then the sum also should be zero, right? But then it means that for some A prime, right? So this will know, right, that this sum is non-zero, but this means by our arguments that A prime also fits B. We are done, right? So we prove that this construction. Okay. So summarizing, so now we have an algorithm, right? So this algorithm is computes the B representative family of size at most A plus B, and it's using at most this number of operations, right? And again, so because I'm working in the finite field, it's much more convenient to speak about the number of operations. It's not exactly the same as what we speak about the running time, right? So, but up to logarithmic factor in the size of the field, that should be more or less the same. Okay, and look, and now we have a completely polynomial time algorithm which computes representative sets. So and this algorithm is polynomial exactly for a very interesting case when A is very large and B is very small. Right, because the previous algorithms which runs in time 2 power A plus B, right, they were not polynomial for that special case. And this is what I want to use in the applications of this algorithm. And applications are in kernelization. So kernelization is a sub area of parameterized complexity, and at first glance, it's trying to achieve something which is impossible. So basically, what it wants to do. So I take some NP-complete problem, right, and then I trying to compress to reduce the size of this problem, right? And at first glance, it's like something completely unrealistic, right? Because take your favorite NP-complete problem, like for example, take SAT, right? And suppose you have an algorithm which for sure guarantees that when this algorithm runs in polynomial time, so you run this algorithm in polynomial time on your instance of SAT, and it's always produce you a new instance with a smaller number of variables. Say even it just reduces one variable. What's happening, right? You have an instance of SAT, you apply a compression algorithm, you obtain a smaller instance of SAT, do it again. Again. Since you have n variables in your instance of SAT, in n steps running your polynomial time algorithm, you will reduce your problem to the problem of size 1, and the problem of size 1 you definitely can solve in polynomial time by brute forcing yes or a no, right? By trying all possible assignments to a variable. So it means that if we have a reasonable compression for NP-complete problem, then we immediately will be able to say that P is equal NP, right? And this is a little bit too much, probably, to ask. So the interesting or a change of the game happens when you say that you want to reduce the size of your problem, but what you do, you are trying to reduce the parameterized problem, and then what you are doing, you measure the success of your algorithm or of your compression, not as a function of the input length, but only as a function of the parameter. And there, actually, you are able to prove some meaningful results, what can be compressed or what cannot be compressed. So I will not go into these details anymore. So I just will give you an example which shows this type of compression. But just if you never saw kernelization, know that what I'm speaking is just a small part of the huge area of research where a lot of interesting and nice problems and results appear. Okay, so the same example, heating set, we already met heating set when I was giving you the algorithm for the first algorithm to compute representative sets. And just to recall again, what is a deheating set problem? I have universe U, I have a family of sets of size D over this universe, and I have an integer K. And then the question is, does there exist a subset X of U of size K that has a non-empty intersection with every member of the family? And on this example, I have an example of 3 heating set. So I have all sets are of size 3. And it has heating set of size 2. So B and G, they heat all the families in this set. Yes, so what I want to do, I want to construct a polynomial time algorithm that takes as the input an instance of D heating set, right? So it's and then its output an equivalent instance of D heating set. An equivalent means it's an instance, and it's a yes instance to the problem if and only if the original instance is also a yes instance. In other words, so this is an equivalent instance of the heating set. So it has a universe U prime, a family S prime, a set of size D also over the set U prime, an integer K prime, And the condition is, right, that the size of the new instance is bounded by some polynomial of k. So universe should be bounded, family size of the family, so everything is bounded by k. So is the problem clear, or there are some questions about the problem? So what I want to obtain. Okay, view it this way, right? So you just you just want to you have an instance of heating set, and you have a parameter k, and then you want to compress the instance to the which size is polynomial of k only. And maybe the question also to think about that. So what I will give you. So I will give you a polynomial time algorithm which is doing this job, and maybe you have to think a little bit why such type of algorithm doesn't show that p is equal and p, right? This is okay. So and again, so the reminder you remember. So when we speak about Bolobash lemma, I gave one of the first examples was about the k-critical graphs. So if you remember, right? So graph is a k-critical if it has a vertex cover k, but for every h, if I delete this h, then the vertex cover of the graph will be k minus 1. And every h is k-critical, sorry, every h k-critical graph, it has at most k plus 1, choose 2 edges. This is what we proved. And then, so I was saying, okay, so how to, so it already gives some intuition why we can compress, for example, vertex cover here, right? Because basically, if I have a, so just give me a graph and give me k, right? If this graph has more than k plus 1, choose 2 edges, right? Then I know that this graph is not k critical. So it means that there should be an h such that if I remove this h, then the vertex cover of this graph will not decrease, all right? So it will remain the same. So then it's like and I delete an h, and this I compress, I decrease the instance size, right? So the only problem is still not clear what kind of h to delete, right? So we know that there exists an h which I can delete, but which h is unclear. So, but just let me do this for heating set. Yes, so the theorem. So deheating set admits a kernel, or in other words, polynomial time algorithm producing an equivalent instance with at most k plus d choose d sets and at most k plus d choose d elements. So this is the statement of the theorem, and the algorithm, of course, is the following. Compute a k representative set S prime of the set S, delete all elements which are not in S prime. Right? Simple like that. Yes, and again, to compute the k representative sets, right, of course, we need to write the set as take a representative matrix of the uniform matroid of rank k plus d. And then, first of all, why this? So why this would be the size of the set will be required, as I claim? Well, because just again, so this is what we proved in our theorem, right? That this algorithm produces a representative set of size at most. In this case, it's k plus d choose d. Right, because every set in the set S is of size d, right, and I'm looking for k representative sets, right? So in total, so the size of the set will be d plus k choose k. Well, and then trivially, right, because it's every set here is of size at most d, so the number of elements in this, yes, and then I also delete all elements which do not appear anywhere, so it means that all elements are covered by this and by this set, and since every set contains at most d elements, the number of elements also will be at most k plus d choose d times d. Okay, so the interesting thing is why the representative set will be the kernel, or why these two instances are equivalent. Well, if I have a set of size in one direction, right? So if I have a set B, which is a heating set of size K for all sets in S, right? Because the representative set is a subfamily of these sets. Definitely, then this heating set also hits all sets in S prime, right? This is trivial direction. In the opposite direction, right? So if I have a set B of size K, which is not heating for the set S, but occasionally if I delete it because I'm deleting some edges and some elements, what happens if this is a set? Could it happen that this set will become a heating set for the smaller instance? Let's see, right? Okay, so if I have a set B which is not a heating set for the original instance, it means that there is a set that is not heated by the set B, right? Or in our language, there is a set A which fits this set B, which fits this set B. Okay, but because this is a representative, because A prime is a representative because A prime is a representative family, right? We know that there exists a set A prime which also fits B, right? But this means that A prime and B are also disjoint, which means that the set B doesn't hit the whole family S prime. Any questions so far? Okay, so the question, can we say that there is exactly one set in A prime for every B? No, 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 no. Unfortunately not, right? Because we know that for every set in A prime, there is a unique representative, or there's a unique guy in B which doesn't intersect it, right? But it's not. Wait a second, what I'm saying. Can we say that exactly one set in AI for every B? But what do you mean? So it means that there's exactly one set in A prime which doesn't intersect B. Yes. Yeah. 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 Then it's yeah. Okay. Now the algorithm for D set packing. D set packing is a kind of dual or to heating set. So input here again is a universe U, a family S of size at most D over U, and integer K. And now we are asking if there is a set of disjoint, if there is at least K disjoint sets in the family S. Right? So in this example, again, that's exactly the same hypergraph or exactly the same set of families. And now, so these two sets are disjoint, right? And or these two, and this is an example where it's a yes instance for K equal to 2. And definitely, the most famous example of a D set packing is for D equal to 2, right? Then it's become a maximum matching in the graph. Okay, so the theorem, so the statement is very similar to what we had for heating set. So the only difference is that the size of the kernel is larger here. So the theorem, D set packing admits a kernel with at most K times D choose D sets, and at most K times D choose D elements. Right? So how to prove this result? Okay, so just to compare, so what's the difference of set packing and heating set? So heating set is a minimization problem, right? We want to find the K, view it this way, right? So we want to make K as small as possible, right? And the D set packing is a maximization, right? We want to find this K sets or make K as large as possible. And the problem, so the difference is for heating set, when we delete edges, right? We will never, if we had a yes instance, we still obtain yes instance. So the only thing, the only where we should be careful, right, that we shouldn't be deleting too much, because if we had a no instance, maybe when we remove ages or sets, we can obtain a yes instance. And this is what we really have to check, right? That was the most difficult part of the proof. For this set packing is completely opposite, right? So if so now what we should care, right? That if we had a yes instance, so we had a k disjoint sets in the original instance, but that after we did compression, that we still have yes instance, right? So now we should be careful that we do not destroy yes instance. Okay, so then and here is the algorithm is a little bit more tricky, right? So instead of computing k plus or a k representative sets, I am computing a larger set of representative sets. So this is a representative sets are k minus 1 times d representative sets. And again, so I compute this family of sets S prime. And then I delete all elements which are not in this family S prime. And again, to compute them, of course, I have to go to matrix representation of the uniform matroid. And again, so the size is trivially, again, so the size of the set is, so I have a set of size D, and then the sets which are k minus 1 times D representative, right? So the total number by our theorem of such of the cardinality of the representative sets is then k minus D times D plus D. So this is a k times D, and then choose D. And then again, because every set contains at most d elements, the total number of elements in U prime is at most this number. So the interesting part, why these instances are equivalent. In one direction, it's simple again. So every k disjoint sets, which are, so if I have a disjoint sets in a smaller instance, the sets still will be disjoint in the larger instance, right? So this is a trivial thing. The other thing is more interesting. So I should be certain that I do not, occasionally, I do not kill all disjoint sets by compressing my instance. Okay, suppose that I have a yes instance, suppose that S has k disjoint sets. Then I take, suppose that S prime is doesn't have k disjoint sets, right? Then I just take a family F of size k of disjoint sets, which has the maximum number of sets from S prime, right? Yes. Now, so if all elements of F are in S prime, right? So, and it means, and F, all elements in F are disjoint and its cardinality is k, right? It means that also S prime also has disjoint set of size k, right? So then, so suppose no, right? Then there is an element, say, or there is a set, say, A in family F that doesn't belong to the set S prime, right? Then I define the set B to be the set of all elements obtained from elements in F by deleting all elements of the set A. Yes. Now, so the set F, it consists of k disjoint sets. Every set is of size d, right? So the size of the set F is k times d. And now I remove one set of size d from F, right? This means that the number of elements in B is k minus 1 times d. Also, because B consists of all elements which are not in B, A and B are disjoint, right? So A and B, they fit. together. And then there is also the set A prime in S prime that also fits B, right? Why? Well, because yes, A prime. Yes, exactly. Yes, there is also A prime in S, which also fits B. Why? Well, just because A prime is a representative set, right? So it should fit B. But then what I'm doing, I'm just taking this. So I'm taking from the set of F, I remove A, and I add A prime, right? Because A prime and A, they do not intersect, right? Sorry. Yeah. No. Yes. Yes. Once again, yes. Because A prime, it doesn't intersect anybody in set B, right? So it doesn't intersect anyone in the set F minus A. So what's happening? I remove from set F one set, and then I added another set, and this is a new set. It doesn't intersect anyone in the set F minus A, right? So this means I remove one set from F, I added another set. So again, I have a set of size K. But the new set, it has more elements from S prime than the set F. And this is a contradiction, right? Because initially I was selecting the set F as the set having a maximum number of elements in S prime. Right? So this is the contradictions, and this shows that these two instances are equivalent. Any questions about this proof? Okay. Yes. So time's running up. So time's running out, and just summing up what happened in all our lectures, right? So the main topic was the representative sets and Bolabash lemma, and basically what I try to convince you that representative sets could be a very handy algorithmic tool, and actually with quite a surprising range of applications in enumeration or exact algorithms and parameterized algorithms. If you remember, we discussed longest path algorithms, kernelization, and actually what I was explaining you the most simplest applications of representative sets, because the world is much more beautiful and wider here. So, and also because we speak about when we start speaking about matroids are very powerful combinatorial tools, and because of the matroids we also are able to, for example, there is a special type of matroids which are called gammoids, and these gammoids, they basically say they speak about connectivity in the graph, and by making use of gammoids people were obtaining quite interesting results about kernelization of odd cycle. And so there's but this is a bit more complicated area of research. Also, when you, because of the matroid power, you can do actually quite interesting things when you do dynamic programming, for example, on graphs of bounded trivets. So there you can start playing with the union and with the intersection of matroids. So there are a lot of things which are still I didn't cover in this lecture, and this is just viewed just an introduction to the area. And if you just were completely out and you just come the last 5 minutes, maybe so the most important take away message, or what is the moral of all these lectures is, right? It's something which I find very amazing, and it's not surprising, right? But it just happened in real life that just sometimes beautiful mathematics has very unexpected applications, because in 1960s, combinatorics was a very abstract field of mathematics, right? Who in 1960s would be thinking that the results from extremal combinatorics, which are completely non-algorithmic, will have applications like 50 years after, will have applications in parameterized complexity or in kernelization, right? Of course, it's not every beautiful mathematics will bring something applied, but this thing's happening, and this is the beauty of life or the beauty of mathematics. It can happen also. So if you prove something beautiful if you prove something beautiful mathematically, don't be ashamed of that it doesn't have any applications, right? It could be that things will happen, right? It's okay. So, and again, so there are also a lot of open problems in the area, and basically, look, so if not you, then who will solve these problems at the end, right? You are the new generation. So just let me just state a few open questions. First of all, so for linear matroids, can we have faster computations of representative sets, right? Or can we prove that this is basically what it is, up, for example, up to, say, some assumption, if you cannot do faster matrix multiplication than we're doing with this omega constant, maybe then you cannot compute representative sets faster. I don't know, but somehow there's no understanding if this if the algorithm which I told you, if its running time is optimal or not, right? This is still is interesting, and it's completely unclear to me. Then also maybe for some special matroids, maybe there will be a faster algorithms for computing representative sets. And for example, so graphic matroids are the matroids. The elements of the matroid are the edges of the graphs, and the sets are independent if they are acyclic, right? So it's like in the forests in the graph. So can we compute representative sets faster than this linear matroid computations? I don't know. And then also the representative, for uniform matroids. Again, so uniform matroids are quite simple, right? So, and it's somehow, it looks a little bit controversial why we have to embed to compute representative sets for uniform matroids or for sets, right? Why we have to represent them as a linear matroids, right? This somehow looks like an overkill, but who knows, right? So it's like and again, so maybe it's maybe there is something which we just don't see so far. And again, so for further readings, for algorithms, for more algorithms using matroids, it's definitely parameterized algorithms would be the book to look for. And if you're interested in more kernelization applications, and if you are interested in how gammoids are applied for kernelization, then that's also, there is a book, and all these books are available for free and legally for free for downloads. Yeah, so yeah. And that's the end of my lecture, and thanks a lot for staying with me. I still have time to answer some questions. Thank you.
Yeah, so I actually have a question about mathematical part. So you have the algorithm to find the representing set of the size guaranteed by Bolobas lemma, but is the lemma in itself true for matroid? So imagine we have sets AI and BI with the property that AI plus BI is independent and for all others are dependent, and we want to get a bound for the size of this family. It's no more true. Only the algorithm exists, or it's what is happening here?
No. It's combinatorial fact, and this is what Lowas proved. And actually, Lowas proved it even for more general, as usual. Lowas is amazing. So what he proved is he proved even for this Q variant of Bolobash lemma for matroids. So it's even more general. Like, and this and he proved it just as a combinatorial fact. right?
But can you then disclose the secret in one sentence? If it's a randomized proof, what is the probability space, and what are the events? So we have a randomized proof for Borobas lemma for sets, and if you have something like this for matroids, if it's probabilistic proof.
No. This I don't know, and this is surprisingly that for matroids all things go through the exterior algebra somehow. It's like it's a
even the proof of Borobas lemma needs exterior algebra, not just induction or something like this.
So no. So there's a variant of Borobas lemma which is called skewed Borobas lemma. So it's there are more constraints on the or a less constrained way how the sets can intersect, and this yes this requires algebra. Whether the
just the same thing you started with, very nice probabilistic proof. And
okay,
it makes full sense in matroids. But is there some proof which can be equally easy or comparable?
Not that I know.
Oh.
So the only the randomized proof they work for sets.
Yeah.
For matroids, I don't know.
Yeah. So what is the value of an algorithm? It's if it's not based on some beautiful simple proof. So it's a pity that there is nothing like this.
I don't know. Well, yeah.
Okay.
I think that this linear algebra trick.
No, linear algebra is okay. Yeah. But
beautiful also. Yeah. No, but yeah, no, I don't know. So and yeah. And again, so probably again, it's like always like when you speak about an NP, right? It's easy to say that there exists something, but if there's not exist something, well, that's why I'm saying I don't know, but yeah. But it's maybe it could be just a nice research problem also, just to get rid of linear algebra and to obtain some really nice probabilistic.
But sorry, but linear algebra assumes the matroid is linearly representable.
Yes.
And the lemma is true for any matroids or only for linearly representable?
No, only for linear representable, of course. No, yeah.
Also, for general matroids, it's just plainly false.
This I don't know.
This original Borobas lemma with AI and BI.
No, for general matroids, no, it's like a. No. For general matroids, yes.
Okay.
No, it's like it's a. I don't see why it should be true for general matroids because
no, of course, but who knows?
No. Okay, maybe no. Okay.
Okay.
My gut feeling will be that it will be just possible to construct to look at some non-representable matroids and to construct a counterexample. But again, yeah, I didn't think about this, Alexander. That's a nice question. Yeah. No, it's yeah. Okay, at least now I understand the question. Okay, good. There is also a question in the chat regarding why kernelization doesn't show P and P. It's because the running time of kernelization is parameterized. No. It's like look, because it's okay. I give you the solution to the exercise. Okay, so kernelization doesn't show that P is equal to P for the following things. For example, so you made kernelization. You obtain an instance of heating set of size some polynomial in K. Right, but still to solve this, how you solve this instance, right? You compress it, but to solve this instance, probably you also will need some time, like 2 to the k, right, or 2 to the some k to the k, or some exponential time in k, right? So, and this is not polynomial running time. So it's so yes, you compress the problem in polynomial time, but still to solve the compressed instance, you still probably need to do. Well, to show that P is equal in P, to show it's in polynomial time. Yeah, that's the answer. Okay, so let me just finish and to thank the organizer for the amazing work and for
Thank you.
We have exactly one organizer, so we should think it's very